Imagine waking up tomorrow morning and nothing turns on. No alarm clock, no lights, no coffee maker humming in the kitchen. You check your phone dead and the charger does nothing. You step outside. The traffic lights are dark. Cars are stalled at intersections, drivers arguing over who goes first. Somewhere across town, a hospital's backup generator is sputtering on fumes. ATMs are blank screens. Grocery store freezers are silently warming, and by tomorrow, the food inside will spoil. Within 72 hours, water treatment plants, which also run on electricity, begin to fail. Cell towers go quiet one by one. This isn't a movie plot. This is what happens in eerie, well-documented detail every time a major power grid goes down for an extended period. It's happened in India, in Texas, in Pakistan, in parts of Europe, and each time within hours, a society that considers itself modern and advanced starts behaving like it's the 18th century. So here's the question nobody asks, because the answer is too good at hiding. What invisible system is working right now, at this exact second, to make sure that never happens to you? Here's the strange part. The thing keeping you alive, keeping hospitals running, food cold, water clean, and yes, your phone charged isn't a single machine sitting in a warehouse somewhere. It's not even located in one place. It is, by most engineering definitions, the largest machine humanity has ever built. And it doesn't sit still. It stretches across mountain ranges, underneath oceans, through deserts, over rivers, into the basements of skyscrapers, and into the wall behind your couch. It's called the electrical grid, and odds are you've never once stopped to wonder how it actually works because it's designed to be invisible. Good infrastructure, like a good bodyguard, only gets noticed when it fails. But here's the surprising part. This machine has almost no memory. It cannot store what it makes, not at any meaningful scale. Every single watt of electricity flowing into your home right now was generated, transmitted, and delivered to you in a fraction of a second, a relay race happening continuously for over a century, without ever truly stopping. To understand how something that big can run that precisely, we need to follow one unit of electricity from the moment it's born to the moment it disappears into your phone charger. Every story needs an origin point. An electricity story usually begins with something spinning. At its core, almost every power plant on Earth does the same basic trick. It spins a magnet inside a coil of copper wire, or a coil of wire around a magnet, and that spinning motion pushes electrons through the wire. That's it. That's the secret behind most of modern civilization. We've just found increasingly clever ways to make something spin. Coal and natural gas plants burn fuel to boil water into steam, and that steam blasts through a turbine like wind through a pinwheel. Nuclear plants do almost the exact same thing, except the heat doesn't come from burning anything, it comes from splitting atoms apart, releasing a staggering amount of energy from a tiny pellet of fuel. Hydroelectric dams let gravity do the work, dropping millions of gallons of water through turbines like the world's largest water wheel. Wind farms skip the spinning via heat step entirely and let the sky do the spinning directly. And solar panels are the rebels of the group, they don't spin anything at all. They use a quirk of physics called the photovoltaic effect, where sunlight striking certain materials knocks electrons loose directly, no moving parts required. Different sources, different fuels, different costs and trade-offs. But here's the part that should blow your mind. All of them feed into the exact same network. A solar farm in Arizona, a nuclear plant in France, a coal plant in India, once their electricity hits the grid, it's indistinguishable. It's not solar power or coal power flowing through your wall outlet. It's just power. Let's follow our unit of electricity. Call it a single spark, born inside a generator at a power plant. The moment it's created, it has a problem. It's too weak and too thick, too high in current, too low in voltage to travel far. If you tried to push it straight into the wires running toward a city 50 miles away, you'd lose most of its energy as heat before it even got halfway there. The same way water pressure drops in a garden hose that's too long and too narrow. So the very first stop on its journey is a step-up transformer, a massive structure standing right outside the power plant, sometimes weighing over 100 tons, built from coils of wire wrapped around an iron core. Its job is almost magical in its simplicity. It takes that low-voltage electricity and squeezes it into a much higher voltage, while reducing the current. Same total energy, different shape, like trading a wide, slow stream for a thin, fast jet. This is where the story becomes fascinating, because now our spark is launched onto a high-voltage transmission line, one of those towering steel structures you've seen marching across the countryside, sometimes carrying electricity at 230,000 volts, 400,000 volts, even higher. Why so absurdly high? Because of a sneaky little villain called resistance. Every wire on Earth resists the flow of electricity slightly, and that resistance burns off energy as heat energy you paid to generate and now never get to use. The amount of energy lost this way depends heavily on current, not voltage. So engineers do something clever. Raise the voltage, lower the current, send the same power down the line, and lose far less of it to waste heat along the way. It's the entire reason those transmission towers are built so dangerously tall. They need enough air gap between the high-voltage wires and the ground and each other to prevent electricity from arcing through the air itself. Our spark races down these lines at speeds approaching the speed of light. But here's a myth worth busting right now. It is not the same individual electrons sprinting from the power plant to your house. Electrons in a wire actually drift remarkably slowly, slower than a snail, in fact. What moves at near light speed is the electric field itself, a wave of push that ripples down the line and shoves the electrons already sitting inside your wall outlet. Think of a tube already packed end to end with marbles pushed one in on one side, and one pops out the other side almost instantly, even though no single marble traveled the whole length. Eventually, our spark approaches a city, and it can't stay at 400,000 volts forever. Nothing in your neighborhood is built to handle that. So it arrives at a substation, a fenced-off facility full of more transformers, switches, and circuit breakers, where the voltage gets stepped back down to something more manageable, maybe 10,000 to 30,000 volts. From there, it travels along smaller distribution lines, the ones you actually see running along your street, not the giant towers but the more modest poles, until it reaches one final transformer, usually a gray cylindrical, mounted on a pole or sitting in a green box on the sidewalk. This is the distribution transformer, and it performs the last and most dramatic drop, taking electricity down to the 120 or 230 volts that your home's wiring can safely handle. Only now, after this entire relay race generator, step-up transformer, hundreds of miles of high-voltage transmission, substation, distribution lines, final transformer, does our spark finally enter your house, race through the wiring in your walls, and arrive at your phone charger, lighting up that tiny charging icon you've never thought twice about. All of that for one phone charge. And it happened in less time than it took you to read this sentence. Here's where the documentary takes a turn, because so far this might sound like a simple, if elaborate, delivery system. But the truly mind-bending part is this: electricity, at the scale a country needs it, cannot really be stored. Unlike water, which sits patiently in a reservoir until you need it, grid-scale electricity has to be generated at almost the exact instant it's consumed. If everyone in a city turns on their air conditioner during a heat wave, the grid has to produce that extra power right then, not 5 minutes later. This creates an invisible, never-ending balancing act, performed by control rooms called grid operators, engineers sitting in front of massive monitors, watching electricity demand rise and fall by the second, like lifeguards watching a tide. Their job is to make sure supply matches demand constantly, because the entire grid runs at a specific rhythm called frequency, typically 50 or 60 cycles per second, depending on the country. If demand outpaces supply even slightly, that frequency starts to drop, like a heartbeat slowing down. Drop it too far, and equipment across the grid can become damaged or automatically shut itself off to protect against it. So operators are constantly adjusting, ramping power plants up during the dinner-time cooking rush, easing off in the quiet hours after midnight, bracing for the predictable spike every time a major sporting event ends and millions of people get up and switch on their kettles at once. Yes, that's a real phenomenon utility companies plan for. But here's the surprising part: this balancing act doesn't just fail quietly. When it fails, it can fail spectacularly, and the reason why is almost poetic in its cruelty. Picture one transmission line, overloaded or damaged by a storm, suddenly shutting down. The electricity it was carrying doesn't just vanish, it has to go somewhere. so it reroutes instantly onto neighboring lines. But those lines weren't built to carry the extra load either. They start to overheat, and to protect themselves, they shut down too. Now even more electricity reroutes onto even fewer remaining lines, which overload and shut down, and so on. This is called a cascading failure, and it can happen in minutes, sometimes seconds. It's the reason a single fallen tree branch in Ohio in 2003 helped trigger a blackout that left 50 million people across the northeastern United States and Canada without power. One small failure, rippling outward, swallowing an entire region. It's a humbling reminder that the grid's greatest strength, everything being connected to everything, is also its greatest vulnerability. Connection means resilience when things go right and contagion when things go wrong. Now, layer in a newer challenge. As more countries shift towards solar and wind power to cut down on fossil fuels, they run into an old problem wearing a new disguise. The sun doesn't shine at night, and the wind doesn't always blow on schedule. A coal or nuclear plant can run at a steady, predictable output around the clock. Solar panels, by contrast, produce enormous power at noon and absolutely none at midnight. So what happens when the sun sets and people get home, turn on their lights, start cooking dinner, and demand spikes right as solar output drops to zero? This is one of the great engineering puzzles of our era, and it's being solved through a combination of approaches. Massive battery installations, some now the size of warehouses, store excess solar energy generated during the day and release it during the evening surge. Hydroelectric dams can act almost like giant batteries themselves. Some systems even pump water uphill during low-demand hours, only to release it back downhill through turbines later, essentially storing energy as elevation. Backup natural gas plants, which can ramp up in minutes, stand ready to fill sudden gaps. And increasingly, software-driven smart grids monitor consumption in real time, automatically shifting loads, predicting shortfalls, and coordinating thousands of energy sources like a conductor leading an orchestra that never stops playing. Before we go further, let's clear up a few persistent misconceptions. Electricity is not stored inside power lines. Waiting like water in a pipe, it has to be generated almost the instant it's used. The electrons that leave a power plant are not the same electrons that reach your phone. Only the push, the electric field, travels that fast. And power plants don't simply switch on the moment you flip a light switch. Grid operators are constantly forecasting demand hours and days in advance, adjusting output preemptively based on weather, time of day, and even television schedules. So where does this invisible machine go from here? The grid of the future is becoming less like a one-way river and more like a two-way conversation. Smart meters in homes now report usage in real time, letting utilities respond to demand with far more precision than ever before. Electric vehicles, oddly enough, are becoming part of the solution rather than just a new source of demand. Some are being designed to feed power back into the grid during peak hours, acting as millions of small, mobile batteries parked in driveways. Home battery systems let individual households store their own solar power and use it after dark, reducing strain on the wider network. Entire neighborhoods are experimenting with microgrids, self-contained pockets of the larger system that can disconnect and keep running independently if the main grid fails, like a lifeboat that can also sail alongside the ship. And artificial intelligence is increasingly being layered on top of all of it, predicting failures before they happen, rerouting power in milliseconds, and optimizing a system so complex that no human team could realistically manage it alone, second by second, across millions of connection points. Some of this is already real and operating today. Some of it is still emerging, being piloted in cities around the world. And some of it remains a vision engineers are racing toward, but the direction is unmistakable. The grid that once simply pushed electricity outward in one direction is slowly becoming an intelligent, responsive network, closer to a nervous system than a pipeline. So go back to that first scenario. Tomorrow morning, your alarm goes off, your lights switch on, your coffee maker hums to life, and you don't think about any of it because you're not supposed to. Somewhere right now, a turbine the size of a house is spinning at 3,000 revolutions per minute. A transformer weighing more than a loaded truck is quietly converting voltage in a fenced-off field you've driven past 100 times without noticing. A team of engineers in a control room is watching a graph of your city's electricity demand twitch up and down, second by second, making invisible adjustments to keep everything in balance. And millions of miles of wire, enough to circle the Earth dozens of times over, are carrying that balance directly into the wall behind you. Every time you charge your phone, switch on a light, stream a video, or ask an AI a question, you're relying on one of the largest, most coordinated, most quietly miraculous machines our species has ever built. It has no single owner, no single location, and almost no margin for error, and yet, more often than not, it simply works. That's not luck. That's over a century of engineering, refined into something so reliable it became invisible. If you enjoyed discovering the hidden systems that keep our world running, don't forget to like this video and subscribe to the channel. We explore the incredible science, technology, engineering, and ideas shaping our future, and you won't want to miss what's coming next.